Thank you, Lou, for that introduction. As Lou said, I'm Ashley Fidler, and my experience with Attosecond and XUV spectroscopy comes from my PhD, which I performed under Dan Newmark and Steve Leone at UC Berkeley. And today I'm going to tell you a little bit about where the field is and where we hope it goes, and perhaps provide some background. So, just as a brief outline, overview of the talk that I'm going to give today. First, I'm going to introduce four-wave mixing. So first, just kind of the basic principles, what it is, and how one typically thinks about it. And included in that, I'm going to talk a little bit about diagrammatic perturbation theory. And then finally, I'm going to conclude that section with a little bit of a discussion of the challenges associated with applying four-wave mixing to attosecond pulses. Then I'm going to talk a little bit about several different experiments that have shown that XUV wave mixing is feasible, and provide a lot of support for the experiments they'll talk about in the next section, which will be about using isolated attosecond four-wave mixing signals. And then finally, I'll conclude with some future directions. So first, what I'd like to point out, although I'm sure that you now know this after listening to Ramon's talk this morning, but nonlinear spectroscopy is a really powerful tool, and it's really something that we want to try to cultivate in the extreme ultraviolet and X-ray regimes, specifically with attosecond pulses. So in both currently attosecond spectroscopy and more broadly, nonlinear processes can be used for a bunch of really important applications. So as Ramon was talking about, it can be used to probe information in the time domain, as in with transient absorption spectroscopy. It also can be used to study one photon dipole forbidden states, or states that are otherwise not accessible with a single photon. And the sort of stereotypical example of that is two photon excitation schemes that allow you to access these dipole forbidden states. And finally, the example that one would think about in the optical regimes and the infrared regimes is where we would use a 2D spectroscopy to really investigate multiple degrees of freedom. So one of the key techniques that underlies these nonlinear processes is four-wave mixing, or more generally, wave mixing. So what one normally thinks about when one is talking about four-wave mixing is you have three input beams, each with their own either unique or distinct or degenerate wave vector and frequency. And they coherently interact with a medium and generate a fourth emission, a fourth beam, where its k vector is defined by the wave vector sum and difference of the wave vectors of the input beams, and the frequency is also the sum or difference of the frequencies of the input light fields. So the way one would think about this is through the macroscopic polarization of the medium. So the way that one really describes these higher order processes is expanding the polarization to include higher order terms. For example, right. So here we have one such example of such an expansion, highly simplified just for convenience, that where the key terms that we're kind of noticing in this equation are the vacuum permittivity, chi, which is the nth order susceptibility of the medium, and E, the electric field, which could be either multiple photons from one very strong field or multiple pulses. So let's go through each of these terms and kind of describe what we would understand from each. So the first, as one would imagine, is your linear absorption, one photon type spectroscopies, which really are workhorses in the frequency domain, and are used as kind of the baseline for what we do. The second term here is responsible for 2 photon processes like second harmonic generation, some frequency generation. While it's the next term, though, it requires a non-symmetric media. So it's not necessarily the most useful if you're talking about, a gas or some sort of highly disordered medium. And finally, this third order term, so 3 inputs, is what we're going to be most interested in this talk, which includes 4-wave mixing and a type of 4-wave mixing, a transient grating. So that is definitely a really valid way of perceiving and talking about a wave mixing process. But from the perspective of the time domain, which is obviously what we're most interested in, given that we are attosecond spectroscopists, it's often better to use diagrammatic perturbation theory, which kind of talks about the evolution of the system explicitly. So first, I'm just going to build up the basics, starting with a kind of just a linear event, and then that can be generalized to a nonlinear event. So let's first set up a 2-state system where we have 2 states, which I've labeled 0 and 1. And when a light is resonant with the difference between those 2 states, we're able to it creates a superposition of those states as described by this wave function here. So alternatively, while the wave function contains all the information you need, you can also describe it with the density matrix here. And some of the key things to note about the density matrix is the diagonal matrix elements and the off-diagonal matrix elements. So the diagonal matrix elements here, which I've labeled in red, are indicative of the ground and excited state population. So the population in the state 0 and 1 in my example here, in my two state system. And then the off-diagonal matrix elements, which will be of utmost importance to us as we go forward here, are here in green. And what they actually represent is the coherence that's generated by the light field. So I've written out what that coherence actually looks like here on the top of this slide. What you can see here is the interesting time dependence really is coming in these off-diagonal matrix elements. So some of the key points to kind of take away from looking at the time dependence of this density matrix is first, the coherence oscillates at the energy difference between these 2 states. And you can kind of see a very quaint depiction of that here. In addition, what I defined are excited state, state 1, to have some lifetime. And the coherence is going to decay with at least twice the population lifetime, which is tau in the way that I have written this. And this isn't surprising if you are more familiar with the optical literature on 2D in wave mixing and 2D spectroscopy. So in that literature, they define these quantities as T1 and T2. So your population lifetime of an excited state is going to be described as T1 here. But it plus any sort of pure environmental dephasing is going to contribute ultimately to the coherence dephasing time. Now, in a lot of gas phase systems, we don't care about pure environmental dephasing, or if we do, it's so negligible, it doesn't really impact our results. I'll often be referring to things just as a coherence dephasing time and going back to that as a population lifetime by a factor of 2. All right, so what the last slide did was describe the evolution of the system without ever really describing how it got there. So a really helpful way of describing how the pulse interacts with the system is by using a double-sided Feynman diagram. And I figured we'd build one of these up together just so we could all feel familiar with it. Because I know some people have seen them before, and some people probably haven't. So first, let's describe kind of the basic structure here. So time is actually oriented vertically on this axis here. And in here, we have two double-sided Feynman diagrams. You'll see that one is the complex conjugate of the other as we build these up. And inside of these two brackets here, we have our Brockhat notation, indicating the density matrix. So at the beginning of our state, at the beginning of our system, before it's interacted with the pulse, our density matrix is in its base state. It isn't excited. There's no population in the excited state, right? So I've just written both of these, indicated that here in the Feynman diagram. Now, once our pulse comes along, we're acting the transition dipole operator on that density matrix, and that's going to generate a coherent superposition. Again, accessing those off-diagonal elements of the density matrix. So when we do that, what we'll do is we'll go ahead and we'll throw an arrow up onto this Feynman diagram, and you're going to see now that this ket goes from the ground state to the excited state. But the other side does not, because you only have one interaction, one photon. Now, the reason that we have two diagrams here is you can act on either side, and they're essentially functionally equivalent, just a difference in sign. And you can throw out the complex conjugate when you're actually thinking about it, but I thought it'd be useful to show. And finally, in this linear process where we only have one photon to give, ultimately the system has to relax back into the ground state, right? So how we depict that is we have some time frame here, T1, that the system evolves over, and then we have this dotted line for the emission of the photon. And this is and we can actually write the entire response of the system, including the explicit interaction with these pulses as such, here as a bunch of stacked commutators. And when we expand these out, you can see we have this expression and its complex conjugate, which is equivalent to this diagram and its complex conjugate. Now, when we include what actually we've described in our density matrix, as per the last slide, we are able to see that this contains all of the information we need in terms of the time dependence as well. We have the coherent oscillations, and we also have the decay, which in shorthand I've now put down as T2. So in order to now think about this a little bit further, just outside of the response, we want to convolve in the electric field to yield the macroscopic polarization. And here we're just talking about the first order macroscopic polarization. But once we've done that, and taken the rotating wave approximation, which I won't go into in explicit detail here, but essentially some of these terms can be thrown out because they don't make sense. For instance, that the excited state would be below the ground state energy. After that, what happens is one can think about the polarization giving rise to an emitted signal by taking the imaginary part of that macroscopic polarization. We generate a new signal that's 90 degrees out of phase from the incident light, called the free induction decay. So we kind of can describe what that actually looks like spectroscopically down here in the bottom. So we have our excitation, and ultimately that results in a free induction decay here, which maintains the same time characteristics, just 90 degrees out of phase as our macroscopic polarization. So you can imagine if it's 90 degrees out of phase with that, we're going to see destructive interference, which is why in our transmitted spectrum, we see a dip and attenuation at those frequencies. And when we take a delta OD, or an absorbance spectrum then and divide out the baseline, that's why we see a peak. So that's kind of the basics from a linear perspective. But the reality is this can all be generalized to any number of pulse interactions. So here I've written out a general form for the nth order polarization, where you can see it's really just convolving the fields and the time frames over which those fields interact with the system with whatever order of the response function you need. Now, since this is explicitly a four-way mixing talk, we'll talk about the third order response function here, which again is, you can see is a bunch of stack commutators, just like the first order response function, just a little bit more complicated. And then we can go ahead and write these all out, and we get a bunch of different terms, which I've just kind of labeled here. Now, so these terms are you can see that R1 is the, its complex conjugate is right below it. And if you look carefully here, you can see that it's just the same stacked interactions, but in reverse. And that's even clearer when we actually look at this from the perspective of the Feynman diagrams. So here we have the double-sided Feynman diagrams for this third order response function. Again, assuming a two-state system. You can see here R1, and then we have this R1, the complex conjugate of R1, and it's literally just flipped interactions. And you can see that we have a variety of different interactions that are possible here, including ones that only occur on one side of the diagram. And we'll see as this talk progresses that these are particularly important in HHG spectroscopy at the moment, or HHG Attosecond four-way mixing spectroscopy. But some of the key rules here, which I think I did mention, but I would like to just emphasize, is that you start completely in the ground state, and at the very least you have to end in a population state. In the examples that I'll be talking about will always be ending in the ground state. Now, in real experiments, we will deal with systems that have more than two states, obviously, and the Feynman diagram representation can definitely take care of that, as you'll see. We'll deal with non-degenerate photons here. They're all assumed to be degenerate. And often, fortunately, constraints in the experimental geometry eliminate a lot of some of these diagrams for us. So that allows us to have a better idea of what's actually going on in the system. All right, so with kind of the basic construction of four-wave mixing out of the way, let's turn to attosecond four-wave mixing. So wave mixing techniques that incorporate an attosecond or even an X-ray XUV pulse are really just beginning to be explored. And you may find that really surprising, given all the benefits that you've heard about previously about using X-ray and XUV pulses and attosecond pulses, right? Like, element specificity, high spatial resolution, probing some of these really interesting electronic dynamics that are occurring on these really short timescales. So the question I think that any reasonable person would ask is why? The answer to that question is well, it's hard, as many things are, but hard, but we're getting there. So the first thing to mention is that attosecond pulses are themselves relatively new on the scene, but they're also it's also important to think about the fact that four-wave mixing techniques, as any sort of nonlinear technique, is going to be very dependent on the intensity of the input beams, including that of the attosecond pulse. This is particularly a problem for high harmonic generated attosecond pulses. As I'm sure you've heard, the conversion efficiency of HHG is typically in the lab pretty low, on the order of 10 to the -8 or 10, and maybe on for some good molecules or atoms, 10 to the -6. But that's really leading to pulse energies kind of in the 1 nanojoule range, which isn't a lot from a nonlinear spectroscopy sort of perspective. Obviously, FELs are a fabulous potential solution to that problem, and that you can get much higher pulse energies, but really their Attosecond generation techniques are very much in their infancy. And there's great progress being made. For instance, this is one of the first papers in 2017 that generated an Attosecond pulse at an FEL. And there's still some issues with intensity and jitter in this particular experiment, but again, it's definitely a way forward, but it's still young. And it's also hard to try to implement some of these things at a user facility where time is so expensive. In addition to kind of these intensity issues, it's also just difficult to implement some of the techniques that are used to kind of isolate and explicitly look at wave mixing signals at these higher photon energies. In part because of, the dearth of XUV optics. It's not as easy to find the optic you need in the XUV as it is in the optical regime. But in particular, one thing I want to harp on in particular, because it's important to this talk, is nonlinear beam geometries, which are often used in the optical and infrared regime to isolate specific Feynman diagrams, isolate specific wave mixing pathways. So here I've drawn kind of a schematic of an experimental geometry, perhaps, where here we have this blue line indicates a pulse of some sort, and this red line indicates a second one. And presuming that red one has enough intensity to actually contribute 2 photons, we have a 4-wave mixing light beam here. And so the ideal is to have this 4-wave mixing signal be separated from the on-axis or pulse, all these other two beams, right? So you can, fortunately, because of the phase matching that I mentioned on the first slide, we can draw this phase matching diagram where our emitted 4-wave mixing light is going to appear at a different angle than our initial pulses. But that obviously depends on what the angle you choose between your two or more input pulses, right? So in that case, it's useful to define not only the crossing angle between the input pulses, but also this divergence angle, which at some distance x will define how far apart to some set point of your input beam and your emitted beam are. So we have this divergence angle, and what it's going to do, it's going to so it describes the separation between the harmonics and the phase-matched XUV wave-mixing signal. So what we can see on this graph is if we plot the divergence angle as a function of the XUV photon energy. Sorry, apologize. If we plot the divergence angle as a function of the XUV photon energy at a specific crossing angle, we see that divergence angle decreases with that photon energy. And that's true also if we use that not just divergence angle, but if we pick some point in real space like the CCD camera. So what are the solutions to this? So first, we can decrease the difference in photon energy between the beams. So that maybe works, right? It depends on what sort of experimental requirements you have. Here I have a diagram that shows a bunch of different you have basically your XUV beam and a bunch of other wavelengths here. And you can see that definitely going to 4.5 EV really does help with the crossing angle, but it's limited naturally. You're still following the same trend. In addition, you could think about increasing the crossing angle between the beams just in general. And that works also to an extent. But the problem, especially when you're talking about an attosecond spectroscopy, is you will have poorer time resolution because of the pulse front wavefront mismatch, right? So here you can kind of see that we have a bunch of beams coming in at an angle, and you can see that the pulse fronts are no longer kind of coordinated. And what this results in is geometric time smearing, which essentially just kind of can ruin your time resolution. So there's a limit. Typically, I'll tell you in these experiments, we're trying to keep it like under 1 degree. So, and then finally, what you could do is you could just let it propagate farther, right? But, you know, that's a solution for people who have a lot of space, I guess, and they can afford custom optics. So whether that works for you or not, I don't know. So given these challenges, though, it's interesting to see what has been done. And the reality is actually quite a lot, given what some of these challenges are. So the first set of things I wanted to talk about in terms of successes are some of the really interesting four-wave mixing signals that have been generated at FELs. Now, these pulses that were used for these experiments aren't yet attosecond pulses, they're femtosecond pulses, but they're really powerful examples of what can ultimately be done now that FELs are able to generate attosecond pulses. It's a matter of time before these techniques are really being implemented there with those attosecond pulses. So the first experiment that I'd like to talk about is an XUV transient grating that was created using two coherent XUV pulses. Again, around 60 to 80 femtoseconds long in an SiO2 sample. So they're able to take two XUV pulses, generate this grating here, and then they actually use an optical pulse as kind of a probe pulse to probe this grating. And what that results in is phase matched four-wave mixing signal. So in addition, what they were able to show in this great paper is that not only are you able to see a four-wave mixing emission from a 2 XUV photon plus 1 optical photon four-wave mixing process, but you get some really interesting time dependence that contains information about the system. So here you can see, here you have their cross correlation and then some long time signal, which is amplified in this panel here. So that long-term oscillatory signal contains information both about thermal relaxation and these longitudinal acoustic modes, which cause the oscillations here. And this is all the way out to 130 picoseconds, so pretty long. But if you look just around time 0 here and subtract out that cross correlation signal, they also see some really interesting and honestly, I think pretty well resolved oscillations there that can actually be ascribed to kind of this tetrahedral bending and some rotation type signals here. So that's really cool. And a really great example of how FELs can really bring this field forward. In addition, more recently, in just a matter of a handful of years, they went from doing it with 2 XUV pulses and 1 optical pulse to all XUV pulses. So the way they did this is they actually split up the beam, just like cut corners off of it essentially. And they had one here that's basically the excitation pulses, and then they have this other one here that's their probe pulse. And so these pulses are about 40 to 70 femtoseconds, they say. So again, still not attosecond. And they're able to change the actual wavelength in order to get different spacings, get gratings on their sample with a different period. And you can see that they get different dynamics when they change that grating period. So here they ultimately get a period of about 110 nanometers, 85 and 28. And all of these signals are related to these longitudinal acoustic modes that we talked about in the last experiment. And decay ultimately due to kind of this thermal equilibration. But the interesting part of this, I think, is that you're really getting out some new information about how this actually works in these systems. So here in this panel, they have a model in blue that plots kind of this thermal diffusion model and what it predicts the decay would be because of that. And then in red, you have what we actually see minus the oscillations, and they're dramatically different by an order of magnitude. So really the thermal diffusion model that one might think about applying really fails spectacularly here. So there's definitely some interesting things to learn with these experiments. And again, while not attosecond, we really are looking forward to seeing attosecond pulses from FELs being used for these sorts of transient grating experiments in the future. Now, outside of FELs, in the lab, we have more room to kind of play around, but at the same time, we have less pulse energy. So a lot of work has been done to see if we can isolate wave mixing signals in the lab, and we can. But first, I'm going to show you an example of how we know that there are wave mixing signals that one can access in the lab. So Roman this morning talked a lot about ATA, so I'm not going to belabor any of this apparatus details or stuff like that. But this is this spectrum here, this color plot. What we have is energy on this axis and XUV near IR delay on this axis. And in the center, we have absorption of a bunch of argon excited Rydberg states between 14.8 and 16 eV. And these were generated in a typical collinear ATA geometry. So just 1 femtosecond, 5 femtosecond near IR pulse collinear with our XUV. But in kind of a, we used kind of a counterintuitive ATA pulse sequence. So most of the experiments that Roman showed have your near IR pulse coming first, initiating some sort of dynamics, and then you're probing it with your XUV. Here we're doing the opposite. So we are probing the evolution of the XUV induced free induction decay. So our XUV comes first, and our near IR is being used as our probe. And that actually creates an amplitude change or phase shift on that free induction decay, and changes the profile of the absorption spectrum. So the key things to see in this spectrum of argon is, first, we have these really fine oscillations here. And these fast oscillations, the frequency of them is twice the laser frequency, so 2 omega. And the way that they can be ascribed is they can be described as the interference of a 1-photon pathway and a 3-photon pathway, where that 3-photon pathway is composed of 1 XUV photon and 2 near IR photons. Now, when in this particular sequence where you have essentially a ladder of photons going up, we're going to call it a ladder type pathway. And what you'll note is, in this case, you have your XUV photon is generating a coherence with these 4s states initially, and they're down around 11.6 or 11.8 eV. And then a dark state mediates the wave mixing pathway, and where to the point where it ultimately emits out of these 4d6s states in this manifold up here. So this is definitely evidence that there is a wave mixing signal, that the XUV and the near-IR pulses can combine in a way that's productive for wave mixing signals. And interestingly enough, that's not the only place where we see that in the spectrum. We also see it up here, these slower oscillations. They're also due to the interference of a 1 versus 3 photon pathway. But the pathway is just constructed a little bit differently. You're actually going down, you're emitting, essentially emitting from this higher manifold down to the 4p dark state around 13 eV. And then we have the absorption of another photon up. So this is something we'll call a B-type pathway. If it's inverted, we call it a lambda-type pathway. But that's, again, clear evidence that we have 3 photon pathways that generate a new signal, an emitted signal. So to kind of summarize this in kind of the terms that we talked about earlier with our Feynman diagrams, here we have our ladder-type pathway. Here it's just a basic energy diagram, but here we have our Feynman diagram. We have our XUV pulse, generates an excited state. A second XUV pulse moves it to another excited state. And during that, between the XUV pulse and the introduction of the near-IR pulses, we have some time delay. And then ultimately we have the emission from an excited state. And same thing, just with the arrows either as an absorption or emission indicated just slightly differently here below. So the key takeaways from this, though, are first, that the broad bandwidth of our pulses here, the XUV, as Ramon talked about earlier, and our near-IR, allows us to access a bunch of different wave mixing pathways, especially in these systems where we have multiple different excited states available for us. In addition, the other thing to note here, as I kind of hinted at earlier, is that these signals all seem to interact on one side of the Feynman diagram. We're always creating a coherence. We never here are creating an excited state population state. We don't have 2-2 or 4-4 here. Now, what this is called is a double quantum coherence pathway in kind of the literature. And so these double quantum coherence pathways, the key thing to think about is that we just aren't creating a population that we're probing. We're always going to be probing a coherence. And the reason for that really is just that the pulse sequence begins with an XUV photon and it has to emit in the XUV. And because you only have one XUV photon to work with, there's a limit to what you can do. Obviously, with an FEL or a much more powerful HHG source, you could maybe do something different, but for now, this is where we're at. In addition, as I said, this time domain measurement, therefore, is going to probe the decay of some sort of bright state coherence. And since all of these pathways of multiple Feynman diagrams will emit at the same energy, it could probe multiple different coherences. And finally, something that I noted a little bit earlier is that all of these pathways are fully resonance enhanced. So that means that there's always a state that's mediating this transition. We're never just putting 2 photons together with no state that corresponds to an intermediate state between them. And that honestly, the reason for that is just because the pathway is so weak without it. Including a resonance there enhances the wave mixing signal exponentially. So it seems that we do really need that resonance enhancement to get XUV wave mixing signals from an HHG source. So once these signals are really noticed, it becomes our goal to do something with them. So this group actually decided to do something pretty simple and clever, really. typically, as Ramon mentioned, you're going to filter out your HHD driver. What they did is they just let it co-propagate through a small little hole in their filter, which created essentially a 3-beam experiment. You have your XUV beam, and then you have 2 near-IR beams now, and they're all collinear. But what this does now is it allows you to, since your near-IR driver and your XUV pulse are obviously going to be coupled and time coincident, you now have a 2-photon excitation, right, which we can describe here, which allows you to actually access a dark state, the dark state that was mediating the pathway, for instance, in our last example. And since now you have a pulse that's delayed from that, your third pulse is delayed over a time t2, you can actually probe now the coherence, probe that dark state's evolution explicitly. So this is a really neat example of that. And the way that they know they actually accomplish that from these oscillations, they see a signal at 1.6 eV or 1 omega. And typically 1 omega oscillations are going to indicate the coupling of some opposite parity states in the time domain, or time-dependent coupling of the opposite parity states. All right, so those are some really good examples, but ultimately we want to isolate attosecond wave mixing signals. So really 2 techniques have been used for that. The first is an energetic technique. So what I mean by that is you try to use the fact that wave mixing signals emit at a particular photon energy that's dependent upon the input beams that you put in, and you try to make sure that it ends up at an energy where you don't have a lot of other things going on. And the way to naturally think about doing that is with your filters. So for instance, I've shown kind of a transmission profile of a bunch of different filters that we have accessible to us in the lab. And you can see that there's some areas where there's a filter that has good transmission, whereas one doesn't. And this has been done in neon. We used a combination of indium and aluminum filters. The indium filter was first, so the light that got to the sample didn't have any, or had very, very little 20 eV light in it. But we had an aluminum filter after the sample. So any sort of wave mixing signal that was generated at 20 eV was able to transmit and be read by the detector. And here you can clearly see that we have signals at 20 eV, indicating that a wave mixing process had actually occurred there, and that those are semi-isolated wave mixing signals. Of course, this isn't really very doable for a lot of experiments. You have to have like the right molecule or the right atom or the right system to study with the right filters. And ultimately that ends up being pretty prohibitive. So the way that we've gone is by using spatial isolation, which is essentially just using the phase matching conditions we were talking about earlier. So the way this actually shows up in our apparatus is that we have a beam, either 1 or 2, depending on the way you've constructed the experiment, your IR beams, and then you cross them with your XUV, and that generates wave mixing signals that are either going to be above or below the harmonics in energy on your CST camera image, where this is kind of just a spatial dimension, and this has been dispersed by your grating. So this also has been done. Obviously, the first time that it was done was on these long-lived Rydberg states in argon. So again, we only had 1 beam here. And what that means is there's a bias depending on the wave mix, whether you're absorbing photons or emitting photons in energy. You're either going to have wave mixing signals above or below your harmonic axis here. So here you can see that we have our 4S states. They're located around just under 12 eV, and then we have a manifold of states up around 15 eV. And you can see distinct wave mixing signals that come from, these wave mixing signals come from up here, And these wave mixing signals actually are probing these states down here. And you can see that here in the time dependence. So here we have a nice long oscillation up in that manifold of states. And as I said, those are coming from two states, our 4s and our 4s prime. So we really just have one frequency, the difference between them. It's more complicated down below at the 11.8 eV-ish range, because you have a manifold of states that are actually being read out. So you have a bunch of different frequencies. Now, just to briefly address some practical concerns with doing this, because I think it's an important thing to know. First, it's important to be deliberate about how you're organizing your experiment, especially in terms of your delay lines. Here we have an experiment where we have two pulses going in, two near IR pulses that are being used for a wave mixing experiment. Now, naively, you may want to put your delay stages in parallel, which is something that often needs to be done for certain experiments. But for the experiments we've been talking about, where you're creating a free induction decay and then following it with two time coincident but differently angled near IR pulses, it actually makes more sense to actually drive the process with just one delay stage and two beams at a separate angle, at a separate crossing angle with the XUV. So it's important to think about that before you actually try to implement it. In addition, spatial and temporal overlap can be kind of hard to get in these experiments, especially if you have a flange in the way and you can't see the sample. So it's useful to think ahead and try to put in some sort of system where you can actually observe and find overlap in a systematic way. The way we did it is we put a pickoff mirror in our recombination chamber right after all the beams enter in. And then we have a detector located outside of the vacuum apparatus at essentially the same focal position as is the target over here. The easiest way for us has been to use a BBO because it creates really large dramatic signals. However, if you want to get the exact angles, it's maybe better to use some sort of camera, like a CCD or a CMOS camera. And there you can just easily use this equation to get out your crossing angle from the fringe spacing on the camera. And finally, just a quick note is that, so in ATA, all your wave mixing signals are going to be what I'm going to call heterodyned. So you have your emission signal and they're on top of something else, your harmonics, which are also themselves perturbed. In a lot of the isolated wave mixing experiments, we're talking about homodyned experiments. So the emission signals are isolated. And that just means that they're not benefiting from the amplification that heterodyne spectroscopies have. So because of that, you might not always be able to cleanly capture your wave mixing signals at the same when your harmonics and absorption signals are present. And that's kind of shown here. You can see there's all sorts of streaking. It's pretty messy. So it's often worthwhile to think about trying to figure out how to mask your harmonics if necessary. And the way we do that in our lab is we've developed a camera holder that vertically translates the camera. And that allows you to just look at these wave mixing signals, which you can see are much, much clearer here and don't really suffer from any artifacts from the absorption signals. All right, so I'm just going to very quickly run through a couple of examples of things you can do. And I think I'm running a little bit late on time, so I'll keep this brief. But I just wanted to show you guys some other things you can think about doing with these wave mixing signals and that maybe have been done. So the first thing is you can use these time-dependent oscillations in the wave mixing signals generated by these broadband pulses to actually get really interesting information about molecules. So here we have nitrogen, and we have this interesting double well dark double well potential here. And what we can do is we can just construct an experiment where first we have a pulse sequence that allows us to probe this inner well pretty well. This inner well is pretty well characterized just by ATA experiments. And we get some oscillation frequency, right? This corresponds to the energy level spacing in that well. However, with a wave-making experiment, you can change the delays a little bit, right? That's one of the powers of wave mixing. So what you can do is you can set a delay so that you find that you're probing the outer well, not the inner well now. And then we have this second near IR pulse is what's actually probing that delayed 2-photon excitation. And here you can see that you get a very different frequency. So this outer well, which actually for this experiment had not been well characterized before, we were able to get a really good representation of what the vibrational spacing in that well looked like. So the key takeaway from that is that you really can obtain key structural information from this, even though you're using an attosecond pulse. But I think we really all want to talk about ultrafast dynamics. So first, we'll just quickly talk about this example as more of in this case, we'll use more as a cautionary tale. So here what we see is you have a ton of wave mixing signals. This is helium gas. And then we have our harmonics along this axis in our camera image. And then we have our wave mixing signals arrayed above and below it. And we have up to 5 orders of wave mixing signals here. But it's important to note when you have this many orders of wave mixing signals that they don't actually correspond to a single emission order. So this is not only 4-wave mixing, and this is not 6-wave mixing. It's really, this is some mix of 4, 6, 8, 10, even maybe 12-wave mixing signals. And what that does is it causes some weird effects. So what we noticed is we were seeing delays between all of these signals in the time domain. When you actually looked at each grading order, you noticed that they were delayed, and that came out in the theory too, from a pretty rigorous theoretical treatment. And the way that one can kind of think about this is hearkening back to these FEL experiments. You have a transient phase grating or a transient grating being created, this time by your near IR pulses, not really by your XUV pulse. And the near IR pulses actually, when they interact with the medium, that has been XUV excited by the XUV, or actually it's causing the accumulation of an AC Stark shift, of a phase shift. And what that does is that in addition to kind of the amplitude grading that naturally comes out of crossing the near IR beams, you're getting a phase grading as well. And that phase grading is dependent on time because it accumulates over the course of the near IR pulse. And that causes some really interesting grading order dependent effects and delays, as well as a lot of kind of non-perturbative effects in the intensity. So that's just something to note, is just carefully monitor how many grading orders you have. Try to keep it to 1 4-wave mixing grading order if you can. Although this is a cool thing that you can do, and it's interesting to think about the ways you could apply some of these non-perturbative effects. And it's interesting you can even get them. But in addition to that, we have looked at decaying states. So here is a camera image taken in krypton. Here we have our harmonics. Here we have our wave mixing signals. Again, we didn't perfectly get 1 4-wave mixing order. We got 4 plus a little bit of 6-wave mixing. But what you can see here is if we look at this and look at this as a function of delay here. So here's delay, here is energy. What we see is you actually have you have emission signals that are both that both contain these oscillatory signals indicative of a coherence, of the electronic coherence that you would expect to make by using such a broadband XUV pulse. But you also are seeing some reporter state, so final state dependent decays, right? So you have a very clear kind of increase in lifetime as the reporter state increases. And the interesting question here in this system is that we have these short-lived ND states that we would expect increase in lifetime as you increase in energy. So this kind of follows that trend. So just naively taking a line out, even ignoring these oscillations, you find that if you fit it to a bi-exponential decay, you're able to extract the correct lifetimes from the literature. So you really are able to probe some ultra-fast dynamics here, if you're being careful. Now, in addition, we've done this in a molecule as well. I just wanted to throw that up there and show that. This is oxygen, where we have some 3s Rydberg states built on the C core here, ion core. And they each contain 2 vibrational levels. And there's actually a difference in the vibration in the lifetimes of these vibrational levels that we're able to observe with wave mixing. All right. And I'm assuming that I am almost out of time. So I will just quickly go on to what we want to do in the future. We want to develop a 2D spectroscopy because that's really some of the most powerful wave mixing technique applications in the optical infrared. We love to be able to explore coupling. And we have done that briefly in a single with a pulse shaping apparatus that essentially is burning holes in our near hour spectrum, but only on long-lived states. So there's definitely a lot of opportunities to improve on this. And finally, we want to diversify our light sources. For everyone who's did all of the talks and we're interested in the light source development stuff earlier in this conference, this is all very much needed for this as well. So it's particularly improving the XUV pulse energies. So with that, I will end my talk. Thank you so much for listening. Here are a couple of resources I found helpful when I was first starting out. And B, if you have any questions, I'm happy to take them.